The Physics in Running by Maria Mendolia, Jamie Ryan, and Melvin Itty. Let's start off by talking about free body diagrams and your center of mass.
Here, F of x represents a horizontal force due to contact between the runner's foot and the ground, known as the propulsion force. F of y represents the vertical force due to contact between the runner's foot and the ground, otherwise known as the normal force. And F of g represents the force of gravity. Here, F of y is greater than F of g, so the runner is technically lifted off the ground as he runs. Running speed is directly proportional to the propulsion force, F of x.
According to Newton's third law, for every action there is an equal and opposite reaction. Therefore, when a runner presses his foot against the track applies an equal and opposite force on the runner. Here we have Melvin demonstrating the runner's stance so we can see these forces acting on him. The higher the runner brings in his knee, the greater the potential energy. The faster the runner, the greater the kinetic energy.
Here the center of mass is represented by a purple dot. Runner's center of mass follows a parabolic arc due to the force of gravity acting on the runner between foot strikes with the ground. The greater the propulsion force, the greater the velocity, and the longer the parabolic arc length, the faster he will run.
Here we see the forces in motion in running. You can see the way Melvin pushes off with his foot and centers himself by swinging his arms. Now let's talk about running with or without swinging your arms.
When arms swing, it helps stabilize the running motion. When a runner pushes off the ground with his left foot, torque is directed to the right, causing a rotation in the runner's body, which is bounced by a counter torque when the runner then pushes off the ground with the opposite foot. This helps keep the body stable and in the proper running position. Bent arms make it easier to run. Without the use of arms, your body might compensate by swiveling the upper body, and this expends significantly more energy than the running with the use of arms.
Now let's talk about running around a curve.
Running around a curve increases race times due to the centrifugal force experienced by the runner as he rounds the turn. The effect of the centrifugal force is more profound in the innermost lane of a track. There is a force countering the centrifugal force, known as the tangential force, Ft, that prevents the runner from experiencing a strong centrifugal force.
Now let's talk about if there is a difference in running inside or outside. On an outdoor surface or track, you apply a forward force against the ground to propel yourself forward. On a treadmill, you must also apply a force in the forward direction to prevent yourself from falling back on the treadmill. Different surfaces may be less strenuous on joints. Treadmills may be a better surface for those prone to injury. Now let's talk about running uphill.
Running uphill requires extra energy expenditure because the force of friction is now present. You do work because the force of propulsion is no longer perpendicular to the gravitational force, and this requires power. Lower force and velocity and a higher impulse than a downhill run. Let's talk about downhill runs. Downhill running requires large acceleration due to freewheeling due to the lack of air resistance. This is the greatest force of a flat or uphill surface. Earth does work here on our body.
Now let's talk about running with air resistance. 7% of total energy expenditure is used to overcome wind resistance of middle distance speed, and 30% at sprint speeds. Running 1 meter or closely behind another runner eliminates air resistance. By closely racing behind, total energy expenditure is minimized and air force is decreased. This is a common tactic used by Olympic runners.
And that's the physics behind running.